This chapter is all about writing functions in function notation, writing function rules, variables, and linear patterns. So today what we're going to do is we're going to talk about different ways to represent data of a given situation. So it says in this lesson we'll begin to see the relationship between two different variables and start to write a function rule to describe those relationships we would see in the real world. The first one we're going to talk about is the tiling business. So here we have a tiling business. It says Anthony Chen's family owns a pool and patio business. In it, they work together to take care of people's outdoor pools and ponds. One of their clients has a very nice fish pond. The fish pond is a square that is 1 yard on each side. So if you notice here, the fish pond is a square, which each side measures 1 yard. The relationship between the square, or the pond, which is 1 yard, and the tiles that you're going to use to create a border around that is that each side of the pond is 1 yard, each of the squares is 1 foot. Okay, the relationship between these two measurements is that there are 3 feet in 1 yard. There are 3 feet in 1 yard. So what we're going to do is we're going to figure out how many tiles does Mr. Chen need to tile this square pool. Okay, so let's first start. Well, if each side has 1 yard, which is 3 feet, let's first do 12 because there's 4 sides. Each side would need 3 tiles. If we were to go ahead and put these tiles on each side, hang on, it takes a little bit. We're going to notice that we don't have enough tiles. So yes, we have 4 sides. Each has 3 to cover it, but because this is a square, we are missing 4 tiles, which represent the corners. So if we do this, this creates the full border around that pond. Okay, so Mr. Chen needs 16 tiles, and our fish gives us a round of applause. Okay, so Mr. Chen needed 16 tiles. What we just saw is a visual representation. Okay, this is called a concrete representation of the pool and its tiles. So if this is our 1 yard by 1 yard pond, we needed 3 tiles on each side because there were 3 feet in each yard. And that represented the 12 tiles we originally had, but then we had 4 corners. So we had to do that as well. Something we're going to touch on tomorrow is independent and dependent variables, but just know that there are 2 different variables in this situation. It's the number of tiles used and the pool length in feet. Okay, if we had 2 variables, we can write a statement relating them. This is called a dependency statement. Okay, in this case, we would say the number of tiles used depends on the pool length in feet. And again, we're going to talk more about this tomorrow. So Anthony decided to draw a model for the 2 smaller versions of the pool and for the larger version of the pool. So I want you to draw a concrete representation to show how many tiles are needed for a 1 by 1, 2 by 2, and a 4 by 4. Just remember, we already did the 3 by 3 and we needed 16 tiles. So go ahead and pause your computer and try drawing. If your drawings match mine, except for my 4 by 4 because I forgot my 4 corners, you should have that you're going to need 8 tiles to tile a 1 foot by 1 foot pool. You're going to need 12 tiles to tile a 2 by 2, and you're going to need 20 tiles for the 4 by 4. this is concrete representation. This is visually what you can see. If we were to fill in a table, we would have another representation, which is called numerical representation. So we just found that if we have a pool length in feet of 1, we needed 8 tiles. 2 would be 12, 3 would be 16, and 4 would be 20. Now, the question is, what pattern does this numerical representation of the problem reveal? Well, every time we've added 1 foot to the pool, we've added 4 tiles to our border. So for every 1 foot added to the pool, 4 tiles were added to the border. Okay. So what this is going to help us do is this pattern and our tables, our numerical representation is going to help us write a function rule. A function rule can be used to determine how many tiles you would need for a pool of 100 feet without having to draw it out. Because if I asked you to draw out a 100 by 100 pool, you guys would look at me and say, oh, you're crazy. So that's not going to happen. So again, we have already seen these numbers, but we have to figure out how we got to them. Now, in the very beginning, I gave you a 3 by 3, so I'm going to start right here. We said that when we were going to try and figure out the tiles to border it, we knew there were 3 feet in 1 yard, okay? And then we knew there were 4 sides. Because it's a square, all 4 sides are the same. So we said that gives us 12, but we were missing something. We were missing our 4 corners. Okay, so you have to have those 4 corners, which is the one time you're going to add those 4 tiles. After you figured out how many you need to actually border the pool, you have to fill in the 4 corners. So we did the same with the 1 by 1. So for every 4 sides, we put 1 tile, but then we added our 4 corners, which gave us 8. Okay, 4 times 2 is 8 plus 4 is 12. And then 4 times 4, because now it's a 4 by 4, plus 4 is 20. So basically what we're doing is we're putting these numbers into the parentheses. But what happens if I give you a variable? If we were to put the variable into the parentheses or next to it, what you just came up with was your function rule. Okay, this is what we would use to solve if we had a 100 by 100 foot pool. So we would say our tiles in the border, T, is equal to our 4 sides times the side length plus the 4 corners. Okay? S represents the side length. Okay? And the number added on represents the 4 corners. Okay? So the one really cool thing now that we have our function rule is there's 3 other representations we could talk about using the function rule. The first one is algebraic representation. Well, we really have seen this one every day in algebra, ever since you've been pre-algebra or algebra. We know that when we're given an equation, we can substitute a value in to get an answer, okay? So if I said how many tiles are needed for a 10 by 10 pool, well, we know that our side length is 10. So we would take this and substitute it into S and solve. 4 times 10 is 40, plus 4 is 44. So for a 10 by 10 pool, you need 44 tiles. Same thing here about a 15 by 15 pool. Well, our side length is 15. So we would take that and put it into our function rule, which is the same as saying an equation, but function rule. And we would say 4 times 15 is 60, plus 4 is 64. So you would need 64 tiles for a 15 by 15. Now, if a customer comes into your company and says, well, I only have enough money for 56 tiles, or I only have 56 tiles, how big can my pool be? Well, we already know what our outcome is going to be. It's going to be 56. But what we're looking for in this problem is what exactly is that side length. So now we're going to substitute into T and solve for S. So 56 minus 4 is 52. When you divide by 4, S is equal to 13. So we would say the pool, or dimensions of the pool, I'm sorry, will be a 13-foot by 13-foot. There's two more representations that we have to talk about. The first one is graphical, and again, we know our function rule. We found it before. We know our pool length, or our tiles in our border, because we already found that. Now all we have to do is graph these points. Remember, this point is like 1, 8. So we would go to 1 on our x, and we would move up 8 on our y. Same thing here, 2, 12. Move over on our 2 to x up to 12, 3, 16, 4, 20. If you notice, it's a pattern, and it's going to go up at the same rate. Okay, so you can use a graphical representation to also predict how many tiles you're going to need rather than solving the equation. The last one we're going to talk about is verbal representation. And this is basically how would you describe this to your friend if they were sick? So we could say for every foot that is added, to the pool, you multiply that number in parentheses, I'm going to say S, by 4 because it's a square. Then you add 4 for the corners. Okay, so this is just a verbal way of writing what you have been doing. Okay, those are all the representations that we're going to look at, but I want to try one more problem. Here's another real-world situation. The Warren basketball team has signed a contract to get t-shirts made for their fundraiser. It costs $25 to work and the company to set up the t-shirt design they choose. And then they have to buy each shirt for $5. How much does the team have to pay no matter how many t-shirts they buy? That's like that one-time setup fee. If you said $25, you're correct. It's not $25 per shirt. It's $25 to set up the machine to make the shirt. It's $5 for every shirt that they make. Okay? So using these values, we can figure out what would the total cost be to the team. Now, like we said, the $25 is one time. You're never going to change that. It's always $25. But even if you sell 0 shirts, you still have to pay the company that $25. If you sell 1 shirt, you would pay the company $25 plus 5, which give you 30. So I want you to take a second and fill the rest of this out and find out how much it would cost the team to buy 50 shirts. So here's what your graph should look like. Notice we have the process column all filled out, and then we filled out, it would cost $275 to get 50 shirts made. So the function rule, let's use variables that relate to this. I'm going to use C for the total cost, and I'm going to use S for the number of shirts. So we would say 25 plus 5 times S. If you switched those, that's totally fine. The last thing we're going to do is we're going to do the concrete representation. I'm going to hopefully get the first 2 drawn. So if nobody buys shirts, you still had to pay $25, okay? But if you bought 1 shirt, you pay $25 plus $5 a shirt. So you can figure the rest of that out. I gotta